Morning, good afternoon, good evening, everyone, from wherever you're joining. Today, we're having a live webinar about beyond Gaussian random effects. I'm Lindsay Florians. I'm an associate scientist here at Pumas, and today we have Dr. Andreas Nowak, our Director of Engineering Research, and Dr. Jose Storopoli, our lead training and education here to discuss this topic with you. Next slide, please. So here at Pumas AI, if you're not familiar with us, we engineer solutions that empower those on the front lines of healthcare. We have two main products that we focus on: Pumas, which is our accelerated drug development software focusing on clinical pharmacology, as well as Live, which is a precision dosing and clinical decision software. Next slide, please. And so today we're going to focus on Pumas, our accelerated drug development software. It's really an all-in-one software that should be start to finish for your clinical pharmacology processes. Next slide. And these are a few of our modules that we offer that should help you in your future processes. So with that, I will hand this off to Jose.
Welcome, everybody. Actually, the one that is going to be speaking first is Dr. Andreas. So Dr. Andreas, take it over. I will be doing the coding in a couple minutes. And welcome, everybody. If you have questions, you can paste it in the chat. We'll be monitoring the chat also. And up to you, Andreas.
Thank you very much, Lindsay and Jose, and thanks for joining this webinar on non-Gaussian random effects. I'll briefly introduce and motivate why non-Gaussian random effects might be relevant to you in a pharmacometric setting, and then I'll very briefly discuss if this is sound at all. I'll not go into much depth there because that is beyond the scope of this webinar. We don't have time for that. Once I've done with that, Jose will take over and give some examples in Pumas so you can see how this works in practice. So first of all, why would you even consider working with non-Gaussian random effects? So one way of looking at it is to look at the Gaussian distribution. So traditionally, when considering mixed effects models, so nonlinear mixed effects models that are typically used in population pharmacometrics, you have a Gaussian distribution of the random effect, which has several convenient properties, but some of them might not map that well to a pharmacometric setting, or particular pharmacokinetics, if we narrow the focus there for simplicity. The Gaussian distribution has support on the whole real line, so it can take any value. The probability might be small for certain values. For instance, if you have a large mean and a small variance of the Gaussian, then there might be a tiny probability of a negative value, but generally it can take any value on the real line. Whereas for pharmacokinetic parameters, that might not be correct. For instance, clearances, volumes, and many other parameters in pharmacokinetics, they should only assume positive values. And some should even be bounded between 0 and 1, which would typically be the case for bioavailability. Hence, because of that difference between the Gaussian distribution and the requirements to the domain of the pharmacokinetic parameters, you can apply transformations to the variable. And typically for quantities like clearances and volumes, you apply the exponential function. So that will map the whole real line to the positive numbers, thereby ensuring that the value of any individual clearance or volume will be positive. Similarly, to ensure that bioavailability parameter lives between 0 and 1, you can apply a logistic map, which will map the whole real line to the unit interval. However, there are some complications that are more or less well known related to this, and they are outlined here. So in the top here, I've given a small Pumas example or snippet of how such traditional modeling of clearance and volumes or individual specific clearance and volumes could look like. So here we choose a clearance and an individual specific clearance and volume, and pick that or draw that from a Gaussian random variable with mean 0 and standard deviation omega CL and VC respectively. To ensure that the individual coefficients that go into the dynamical system or the ODE ends up positive, we apply the exponential mapping to the etas, as you can see in the pre-block, the middle of the code snippet. That is then multiplied with the typical values of the clearances, of the clearance and the volume. So this is meant to capture that overall you have a population that averages around theta CL in clearances and theta VC for the volume. And then some of the individuals will have a higher clearance and some will have a smaller. However, there is a slight complication in the interpretation here in the situation where the variability is rather large. So as you can see, the expected value of this individual clearance parameter is actually not theta CL. It is the exponential of the logarithm of theta CL plus a term that is that depends on the variability. For small variabilities, that does not matter. So in the situation where you have, say, 10% variability, the expectation is effectively the same as the typical value that you pass into the model. I have given examples in the table to the right where you can see different values of omega, so that it corresponds to 10, 20, 40, 80, and 160% variability in the typical interpretation of the omega, and then the associated mean of the clearance. And this is under the, for all these values, the theta CL, the so-called typical value of clearance, is a half. So you can see from for 10 and 20% variability, that is a good approximation. There's a good relationship or a clear relationship between the expectation to the clearance across the population and the typical value of theta CL. They are all around 0.5. However, if you end up in a situation where larger variability is required, then there'll be a quite significant deviation between the population average of the clearances and then what you consider the typical value. So you can see it grows to 0.54 if you have 40% variability and up to even 1.8 if you have a very large value of the variability. That can happen in some applications. So that means that the way you interpret the theta value might be quite wrong from what is actually the mean value across your population of the clearances. One aspect that might be reassuring here is that the median of the clearance is still theta CL. So you can say maybe that you aren't too bothered with this fact because the median stays around theta CL. But typically in this kind of modeling, we actually care about the expectation, and that is there the association between the mean and theta CL is only holds well for small values of omega. Another important quantity is the coefficient of variation of the individual parameters, and you can see here that it is the square root expressions, the square root of expectation of omega squared minus 1. And that is a key property of why you'd like to use this model, because typically it is considered the case that you have a constant coefficient of variability in the data, right? So when the mean of the data grows, then you also expect to have a proportional growth in the standard deviation. And the log normal, as you get when you take the exponential of the normal distribution, has this property that the coefficient of variation is constant. However, the relationship between the parameter omega and the coefficient of variation is not straightforward unless you again have small values. So for small values of omega, this square root expression essentially collapses to omega CL. But for larger values, the exponential will dominate, and the coefficient of variation will be quite a bit larger than the first order approximation will show. So that's one example where the traditional modeling of individual parameters might result in some surprises or deviations between what you think is the typical value and what is actually the typical value, to the extent that the mean is the typical value. There is an alternative though, but that is only available if you have more freedom in choosing the distribution that you for random effects. One popular distribution for models with a constant coefficient of variation in statistics is the gamma distribution. Here, it's useful to consider parameterization of the gamma distribution where you model it with the mean of the distribution. So it's called mu sigma here. However, there are several parameterizations of the gamma distributions around, and the one in Pumas is a slightly different parameterization where the parameters are the shape and scale parameters, but there's a simple relationship between the different parameterizations. So you can see it here, the mean parameter mu is equal to theta k times k in the Pumas parameterization, and the sigma is equal to 1 over the square root of k. So here there's a small code snippet as well that is trying to model the random effects in a very similar way to what we saw before. So effectively, the random effects here for CL and VC are the same as we saw before. They are very close. They are thought to kind of model the same mean and the same coefficient of variation. But instead of using a log normal, we now use a gamma distribution. So I've written out the two quantities that we talked about here. So the expectation of the clearance value variable is now theta CL. So you have this direct relationship between the expectation of the clearance random variable and the typical value parameter. Now it does not depend on any other parameters. It is a direct relationship between the expectation and the typical value parameter. And the coefficient of variation is also simpler. It is simply, oh, sorry, there's a small typo, omega CL. The sigma up here should have been an omega, so I'm sorry about that. So that's one example for the typical pharmacokinetic parameters. Another clear motivation for this is the bioavailability parameter, because that is supposed to be between 0 and 1 in typical applications for various reasons. But with a traditional Gaussian modeling, that might not be straightforward. If you use a log normal transformation or the exponential transformation to get a log normal, then the random effect will effectively take values on the whole positive axis. So you have no assurance that the random effects will stay between 0 and 1. It can in practice might be the case if you have a sufficiently small value of the variability parameter. However, you would really like to, often you would really like to enforce that this value stays between 0 and 1. And as mentioned on one of the previous slides, that can be enforced with the logistic transform. With the logistic transform, you'll get what's typically called the logit normal, because when you apply the logic transformation to the random variable, you get a normal distribution. So that is kind of similar to the exponential transformation that we saw earlier. And it also has a kind of a similar drawback. So suddenly the expectation of your buyer availability, individual buyer availability, will no longer be the same as the typical value parameter for your buyer availability. So for small variability parameters, maybe, or variances of the underlying Gaussian distribution, you'll again have a close relationship. You can see a similar table to the one I created before, that for 0.1 and 0.2 omega values, you effectively have an expectation of the individual buyer availability that corresponds to the typical value parameter that you pass into the model. However, if this variance or standard deviation parameter for the underlying Gaussian distribution grows, then you have a departure from the typical value in the individual buyer availability parameter. So in particular, if this underlying variance grows very large, then you can have a significant deviation such that the buyer availability on average is quite different from the typical value. The same result holds as before, such that the median will not deviate from 0.8, but again, it's not clear that you prefer the median over the mean. So if you want to model the mean, you'd have to consider alternatives. Thankfully, there is one if you allow to use an open-ended set of distributions for the random effects. And in Pumas, you can use the beta distribution. So that will be an alternative if you want to model the mean of a buyer availability parameter that stays between 0 and 1, because the beta distribution lives on the unit interval and is a very flexible distribution. It also comes in a couple of parameterizations. For this kind of regression modeling, the parameterization in terms of the mean mu and a dispersion parameter phi is most convenient, but the Pumas standard parameterization is in terms of alpha and beta. But again, there is a simple relationship between the alphas and the betas and the mu's and the phi's, as you can see here. So there's a small code snippet here showing how such a modeling could look like. So here, theta f is the typical value of the buyer availability, and when you're using a beta distribution, you have the direct relationship that the expectation of the individual specific buyer availability is theta f. There's now a closed form solution, and it's a direct relationship. It's not depending on any other parameters. And just for to explain the role of the phi parameter, you can see the variance of the individual specific buyer availability. It is a kind of a binomial variance, so it's theta times 1 minus theta, and then you have this denominator where phi is included. So the larger phi here, the smaller variance or more precise buyer availability you'll have. So that's an example of how you can use a non-Gaussian, another example of how you can use a non-Gaussian random effect to model a relevant quantity for pharmacokinetic models. So I will stop the motivation here, and briefly, before handing over, I'll briefly talk about these from a kind of a statistical point of view. It'll be very brief because it's a deep topic. But you might ask if deviating from a Gaussian distribution is sound. Will the statistical properties of the analysis still be true? Because you might think that the Gaussian distribution is key for the Laplace approximation to hold true. To discuss that, let's summarize. When is the Laplace approximation exact? That is the case if you have a Gaussian error model. You have a Gaussian random effect, and you have a linear relationship between the random effects and the conditional mean of the model variable. So that's a very restrictive setting. So it's kind of the classical mixed effects setting, but that is rarely the case in, or it's never the case in pharmacokinetics modeling, but sometimes you have, of course, can have PD models where this standard model is used. But in all PK models, it's these assumptions are not satisfying. You might have a Gaussian random error model, but effectively you will not have a Gaussian random effect because of the exponential transformation that you showed before. And then after that, you're also solving an ODE. So you're having a lot of non-linearities that will make the Laplace approximation non-exact. So that means that the Laplace approximation is then an approximation, and it can be good and it can be bad, but it is an approximation. However, it can be asymptotically valid, meaning that as the number of observations grow, it will become better and better typically. But it's important to keep in mind what dimension the number of observations need to grow in. So it will be in the time dimension, and it will also need to be in the part of the concentration curve where you have movements, right? So adding a lot of zero concentrations at the end would not improve the approximations, for instance. And if you have occasions, it will be as the number of observations within an occasion grow. But typically, if you would then have that the approximation improves. But of course, for small values, you can have a significant deviation between the approximation and the exact likelihood. With that, I'll hand it over to José to give some examples, like coding.
Thank you, Andreas. So, folks, before we dive into the code, any questions about the motivation, introduction, and mathematical, statistical intuitions, why you want to use random effects? Feel free to either open the mic, this meeting is being recorded, or post it in the chat. The chat will not be recorded, so you can express your doubts, your questions, whatever you like. Okay, let's dive into the code then. Let me share my I think I need to share a window to have my sound. Can you see my screen and also hear me?
Yes.
There's a great question by Christopher Mayer. Can in principle we use any of the distributions from distributions.jl? So folks who don't know, we have a package called distributions.jl. This package is inside the Julia Stats ecosystem, and Pumas uses this distribution.jl under the hood. You can use some of them, but not all of them, because we have some distributions. I think it's under overview of Pumas, I guess. And there is a place where we list all the distributions that you can use. There you go. So we can use all of those distributions. If you want to use a custom distribution in Pumas, you have to define the median, how do you sample, and also how to take the log PDF. I guess that's it, right, Andreas?
Yes, I think that's it. Then it should
Yeah.
work. And if it doesn't, then please let us know.
But all of those distributions you can use. I mean, you can use, I think we have von Mises here, I guess. No, we don't have von Mises, but we have gamma, exponential, chi-square, cosine. We have a lot of distributions that I never heard of, like by weight, for example, beta prime, Kolmogorov distribution also. You can use any of those. And before I dive into the code, I think that there is one thing that I want to point it out. I think that Andreas and Lindsay haven't touched that briefly, is that why use random effects, non-Gaussian random effects? A lot of people doesn't use Gaussian, only use Gaussian random effects because either by sociological reasons, because that's what everyone is using. I don't know, their bosses or their team only uses Gaussian random effects, or their research group, their advisor. So you can broke from the Gaussian random effects. You can break free. You can use other ones, and also some software that you are constrained to using cannot do other distribution from random effects besides Gaussian. So that's one more thing for you. One more advantage of Pumas is that you can use whatever distribution you want to for maximum likelihood and also for Bayesian. And if you are an academic, Pumas is free to use. Or if you are in a company, you belong to a team of that does pharma-related modeling, PKPD modeling, please contact sales@pumas.ai to see all the advantages and get a demo from us. There's another question. What is the advantage of using beta compared to a logit transformation of random effects? I will cover that in this file, but the idea is that the beta, as Andreas pointed out, the beta distribution, when you condition your random effects in a beta, instead of transforming the parameters, if your random effects are big, like they have large values, you could shift the mean of your bioavailability parameter. You can shift it away from the true mean, just because instead of using another distribution as random facts like the beta, you are using a transformation of normal distribution, and that can have some impacts, and that can shift away the mean of your parameter, the global, the fixed effect mean, if the random effects are very big. I think that's the main advantage. Okay, so let's start diving into the code. The code and the slides, they will be available for you. We are going to send them using to the same email address that you sign up for this webinar. So I'm just going to load some packages. I'm loading Pumas utilities, because I want to compare some models. I'm reading also data from a CSV file, so I need CSV and data frames. And I have some models that I define here. So this is the first model. This is the traditional model. And this is the traditional one, where we use Gaussian random facts, normal random facts, and we do a transformation. We exponentiate them to constrain them between 0 and infinity. And this is an open interval, so 0, we don't have any mass at 0. This is the main issue behind the normal and log normal parameterizations. So here I'm define the model traditional. And this is the parent block. We have a typical theta for clearance, a theta for volume, and also random effects omega for clearance and volume also. And we have a random term, an error term, sigma here, and this is being parameterized by standard deviation, so it's just sigma, not sigma square. In the random block, we pretty much draw our etas from a normal distribution with mean 0 and standard deviation, the random effects for both clearance and also volume. If you are doing like multivariate, that would be a multivariate normal, but the extension from multivariate is pretty much similar. In the pre-block, we define clearance and volume as the thetas for clearance and volume multiplied by the exponential transformation of the random effects to positively constrain them to be between 0 and infinity. And in our dynamics blocks, this is a simple one compartment model. We have a central one and the central, the derivative of the central is a function of the ratio of clearance and volume times the compartment. And finally, in our derived block, we define our mean concentration as a deterministic assignment of the central divided by the central compartment divided by volume, and we condition our concentration as a likelihood of a normal distribution where the mean is CP and the standard deviation is sigma. So this is a basic model, and this is the traditional one. Now we go to the, and let me just run this code. Now we go to the direct model, where we model random effects with a log normal. We don't need to exponentiate anything. So in our random block, we pretty much say, okay, our clearance and volume, they are pretty much, the random effects are derived from they are sampled from a log normal distribution with a mean log of theta CL and standard deviation omega CL, both for clearance and for volume. So in the pre-block, we don't need to exponentiate anything. We just need to redefine CL and VC so that we can use in our dynamics block. And the derived block stays the same. So the only thing that changes here is the random and pre-blocks, because the random effects come from a log normal distribution, and I don't need to do any transformation in the pre-block. I just make like CL equals CL, like an identity operation here, just to have CL and VC available to be used in the dynamics block. That's why we do this in the pre-block. Now let's go to the gamma model. The gamma model has one nice advantage from the log normal model. It's because that gamma, we can have density. We can have density at 0. So the log normal distribution doesn't have support at 0. So if you have something with 0 as mean in the log normal distribution, that blows up, that is minus infinity. So that doesn't give any support. And the gamma is a little bit more flexible, that we can have also positive support as 0. And also this directly models the mean. So as the question that we just answered, and Andreas also showed that in his slides, if the random effects are big, using a normal and exponentiating the random effects, or directly using a log normal as the random effects, you could have the mean of your theta clearance and theta volume, the mean of the fixed effect parameter, being shifted away from the true mean. So that's a problem, and we can fix that with a gamma distribution because you can directly model the mean, and the mean is not sensitive. The true mean of the fixed effect is not sensitive to larger values of random effects. So here the parent block, it's pretty much the same, and the dynamics and the right block are also the same. Only thing that changes are our random block. So now we are sampling CL and volume random effects from a gamma distribution using the parameterization that Andrea showed in the slides. And this parameterization gives pretty much the same. So these three models, they are similar. They are equivalent if the random effects are small. If you have random effects are small. Sort of Turing, there's a question in the chat. Is this basically Turing under the hood? Sort of. If we have this parameter not being like real domain, and we have something like the parameters have a prior, then you have a Bayesian model, and it's going to call Turing under the hood. That's how Pumas works. But now it's not Turing. We use the sum of the ideas from the Turing domain language, how we specify this distribution and how we specify likelihood and priors here. But this is not a Bayesian model. This is a maximum likelihood approximation iterative model, either by first order condition effects or by Laplace approximation. But the same model with small changes, just change the parent block, I can do a Bayesian using Turing, and that Pumas calls under the hood. But that's a great question. So this is our gamma model. Now I'm going to just skip ahead and show you that the true parameters that we simulate data. I have a CSV file for the simulate data, but the true parameters are this one. And one thing that I want to note is that the true parameters that we simulate data, this is a synthetic data, the omegas, the random effects are small. So those three models should give the same parameter values for fixed effects, theta CL and theta VC, the theta for clearance and the theta for volume. So let's pretty much, we read the data here. We have a CSV file with, I think it's 10 subjects and one dosing event. Oh, let me show it to you. So let me read this. And if you take a look at our data frame, we have 7 data points. We have the dosing effect, so it's times 0. And then we have the dosing event is times 0. And then we have 6 data points from 0.5, 1, 2, 3, 4, 5, 6 hours, and we have 10 subjects. So that's our simulated data. And we define a population from this data frame. We're using the read Pumas, and we do a fitting of the models with fit. And we are using just the initial parameters for every model. So this is our traditional model, and we are using FOCE as an estimation method in the 4th positional argument. So we do this for the traditional one. We do this for the direct and for the gamma. And there you go, it fitted. So when we do compare estimates for all of those 3 models, you see that they pretty much arrive in the same parameter values. But if our random effects were big, so not the 0.1 that we simulated from the true parameter values, we would see changes in theta CL and theta VC. So the gamma would be would represent much more reliably the true mean of the underlying fixed effects than the normal and log normal. So that's the advantage here. I'm just showing that it doesn't hurt for you to do like alternative parameterization. It can only do it can only do advantages. It can only do good, because if your underlying random facts are big, your gamma distribution will recover the true mean of your fixed effects. So that's how you do in a typical, in a classical PK model. That's how you do alternative parameterizations for the random facts. Besides Gaussian, you can do it log normal, or you can do it the gamma. And those three, we think that the gamma is the most advantageous one, because if the random facts are big, the gamma will recover the true mean of your fixed effects. Any questions in this code, the PK code? So now let's go to the BA model, the bioavailability model. And this is a two-compartment model where we have clearance, VC, and theta Ka. And also we have a bioavailability parameter here that we are constraining to be between 0 and 1. And we also have random facts for all of those thetas. And as Andreas showcased in his slides for the gamma distribution, we have a phi parameter that's an alternative parameterization of the beta. That's a dispersion parameter for the beta. And then we do random facts, and we do log normal for all of those parameters. We can also do a gamma here if we want to, but just to make it simpler, we did a log normal. And we also have a bioavailability random facts parameter that's a beta parameterized with the dispersion parameter phi here. So the alpha in the beta is the mu of the bioavailability times phi, and the beta parameter of the beta, sometimes it's called A and B, respective, depending on the literature and what textbook are you seeing, or wiki page are you seeing for the beta distribution. But the beta or B parameter is pretty much 1 minus the mean of bioavailability times phi. So the problem here is that if we do it a logit normal transform of this random facts here, we also get, if the random facts are big, so if this phi or any of the other omega parameters in our model, random facts, they are large, this bioavailability, this data bioavailability will not be unbiased. It will have a bias from the random facts if you are using a logit normal transform. So pretty much a logit that scales everything to between 0 and 1. So and here we don't have to worry about this, because it doesn't matter if our phi is large, the beta, if those parameters alpha and beta from the beta distribution are large, are, I don't know, over 1 or over 100, it doesn't matter, because the beta will always be defined, constrained between 0 and 1. So that's pretty much what we want in a bioavailability parameter. And we also have a dose control here. And our pre-block, we don't need to do anything. We just do the identity transformation of our parameters to be used in our dynamics block. It's a two compartment model. And we pretty much do the mean concentration is a determinist assignment of central divided by VC. And our concentration is conditioning on the likelihood of normal distribution with CP as mean and sigma as standard deviation. And I read the data. this is also 10 subject data. It's a crossover design. So we read the population data. We read into a population with the read Pumas from our data frame. And when we fit our model, let me just pop up my terminal here. So when we fit the model and we recover the true parameters, let me have, okay, so I might need, yeah. So when we recover the true parameters, we can see that, of course, we do have 10 subjects. So most of those parameters, they are not exactly the same, but they're pretty much similar. Or if we had more sample size, a bigger sample size, our likelihood would be much more informative. And we would have recovered the true parameters from our simulation. And our simulation, we had this parameter here, this set of parameter. So you can see that we get pretty close to our theta bioavailability parameter, fixed effects, and our random effects are also close, not close enough, but mind you that we only have 10 subjects. So maybe in a bigger sample size, we would would recover the true parameters for our data and our model. So that was it. How you use non-Gaussian random facts in two contexts, one a PK model and another bioavailability model, two compartment model with a crossover design. Any questions so far? Okay, I guess we don't have. Oh yes, we do have questions. Yes, we can get a confidence interval. There's a function in Pumas called infer, and with infer you can pass the resulting object from a fit function. So that's what we call a Pumas fitted model, and you can choose. You can do like traditional confidence intervals using the sandwich estimator or using the inverse Hessian, or you can do bootstrap, or you can also do SIR, that's sample from importance, sampling from importance sampling, resampling. So you can pretty much do either bootstrap, SIR using importance sampling, or you can do traditional stuff using either the sandwich estimator or the inverse Hessian. We typically see deviations when you go like over, I think it's 0.8 in your simulations or in your table, Andreas. Correct me if I am wrong. I think it's from 0.8 onwards, we start to see some deviations from the true mean of the fixed effects.
It's a gradual movement away that is being kind of accelerated, of course. So it depends on also your kind of tolerance, how far away you consider too far away. But yeah, you can calculate these in particular for the log normal case where you have a direct formula for the relationship. In the logit normal case, it requires a numerical integration to do the calculations of the deviation.
Does sparse sampling or the number of subjects plays a role?
Yes, it does.
Yes.
That was kind of what I hinted at in the end, because when you have a nonlinear and non-Gaussian model, so it's when you have a likelihood function, log likelihood function that is not roughly quadratic in the random effects, then you need a lot of subjects for it to be approximately quadratic. So if you have sparse sampling, then you don't have, then the asymptotics will not kick in, right? So it is to be expected that you have a larger difference between the approximate likelihood and the real likelihood if you have sparse sampling. So ideally, it would be great to have a methods available that can integrate out more accurately, and that is also something we are considering. But it's also more demanding. In particular, it's also pretty costly if you want to approximate more accurately than what's possible with the Laplace approximation.
Just to showcase once more, Pumas AI send us an email at sales@pumas.ai. We have Pumas for Enterprise and also have Pumas for Academia. So if you are a research student and faculty, Pumas is free to use. You just need to register. If you want to get a code or a demo for Pumas for your company or for your working group, you can also please contact us. We do have a paper that we are presenting at ACOP this year that compares benchmarks between Pumas and traditional and other very well-established software solutions for PKPD. And we showcase that we are as exact as them. And in almost all of the cases, we are faster. We are way faster than the traditional well-established softwares. And of course, this syntax here is way more friendly. Also, I can type in data, and this is much easier. And I can do the data wrangling and the plotting and the modeling in the same tool. So one tool to do everything. So that's it. I'm going to pass over to Lindsay.
Thank you, Jose and Andreas, for talking today. If you are interested, we will be having another webinar on May 31st covering the first order methods for non-Gaussian nonlinear mixed effects models in Pumas at the same time. I will put the registration link here in the chat, but it will also be posted to our LinkedIn page in the coming days, as well as our website. So if you have any other questions, we'd be happy to answer and stick around for the next few minutes. But otherwise, have a great day or evening wherever you're located.